Hello everyone and welcome to Handmade Hero Show, where we code a complete game live on stream. Before we get started today, I just wanted to put in a brief little aside on LZ versus run length encoding compression. The fine fellow who is responsible for the past episodes, this past episode guide that we use on Handmade Hero, is currently working on a run length encoder, and he was mentioning it in the pre-stream, and I was just mentioning that, hey, if you make a run length encoder, it's not that much of a jump to making an LZ encoder. The decompressor is actually basically the same, and it's only the compressor actually that gets a little more complicated. But I wanted to diagram that for folks because there's a really interesting thing that happens with LZ compression and run length encoding that I thought would be interesting for beginners here. So let me just go ahead and sort of diagram that out. So let me just talk about RLE versus LZ. All right. So for those of you who don't know very much about these sorts of things, which by the way is also me, I'm not a compression expert, as I think I mentioned at this recent Handmade Con. One of the reasons I asked the folks at RAD to come and talk about it is because they are compression experts. I might wager to say they are the compression experts. As like the the people who currently have like the world's reigning smallest size, fastest speed compressor or whatever it is. But you know, just some basic things here, because compression is kind of just interesting and encoders are interesting in the general case, and there's some simple things you can start to look at about them. So what are these things? Well, you know, if you imagine that you're sending something and you or encoding something that you want to make smaller, right? There's a number of ways that you might go about doing this, and you know, every way that you might try to compress something is basically about figuring out what special properties of the data are that you're working with and exploiting those special properties. Because in general, you know, like I said, I'm not a compression expert, but the general consensus among people in terms of the math on this is that information theory-wise, in terms of what we've been able to determine about how information really works, it's kind of provable that there is no way to generally compress things. Meaning, you know, if you wanted to make something that can fit stuff in a smaller space always, it's not really possible. All you can do is make things that fit things in smaller spaces for certain classes of information, right? And again, like that's, you know, math as we know it seems to indicate very strongly that this is the case. And, you know, I mean, who knows, maybe someday we'll come up with weird things that sort of change the way we think about the world or something. But assuming that the math we currently have is you know, as infallible as we currently think it is, then there's nothing you can really do to make a thing that generically makes information smaller. That just doesn't happen. But with any piece of information, usually you're transmitting it in a context, right? Like, for example, maybe I'm making an image compressor. Well, that means that I kind of fundamentally know I'm transmitting images as opposed to other data. So that already puts me in like a class of sort of information, or storing them or whatever I'm going to do, right? And similarly, maybe I know these are photographs. So there's even more restricted the kinds of sort of information that might be in here and the way that it looks. And so typically what we're doing with a compressor is we're saying, well, for the particular category of stuff that we're working with, what we're going to do is say we know that the type of information we're compressing has certain fundamental properties that are often true. And by exploiting the fact that those things are more often true than not, we can encode the information in a smaller space, because we are effectively giving up the ability to encode other pieces of information that are not relevant to our interests in this case. Those would get bigger, right? So if you imagine this playing out in a scenario like I said with image compression, let's say we're trying to losslessly compress an image. Well, we kind of know the sorts of images humans tend to make and transmit or store. Again, we also know photographs versus like line art or that sort of thing. These all have very specific properties to them. It's very unusual that someone would make an image that's just like white noise, right? Or an image that's just like a very specific weird pattern of alternating dots or whatever. Those are very unusual images. So by saying that we don't care how big those images are to encode, we can make a bunch of sort of assumptions about how our image data is going to look that will allow us to encode the images we more frequently care about in smaller space, right? So that's generally what we're talking about when we talk about compression. It's this sort of selecting a sort of an area of information that we care about storing, and we're pre-saying we're only going to work well on those things, and then we start to make a bunch of concessions to that type of data that means that other types of data would get bigger, and we'd actually have an inflator, not a compressor, if we ran it on those. But since we never care about running it on those, it's OK. And that's basically what compression is about. It's about baking those assumptions in to a piece of code that then allows you to store and transmit a certain class of information, often much more efficiently, because you've sort of given up on these others, on the other classes of information that you don't care about. And so RLE, or run length encoding, is usually the first kind of compression that anyone comes across, and it's the kind that you used to use way, way back in the day before sort of more extensive compressors were really common. But all it is it's called run length encoding. And what it is, RLE schemes are a family of schemes that all work very similarly, but the specific way that you might pick how to encode them might change a little bit. But the idea is simply that, well, if I'm encoding a piece of data, that has some data, maybe it's got, an A, a B, a C, an E, a G, an H, and then an A again, and then a B, and whatever, and it comes through here, and that's my message. But then it does something like, well, now there's just a bunch of B's in a row, right? And you can imagine this sort of thing is a little bit more popular perhaps in pixel art, where you've got maybe big fills of the same color or something like this, right? Well, what run length encoding does is it says, all right, if I'm going to encode this message, well, and the unencoded version of this message, right, how many are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So there's 16 sort of pieces of information, or symbols, if you will, in this, this piece of information that I'm trying to encode. But 1, 2, 3, 4, 5, 6, 7, 8 of them, right, are actually sort of information that I would have to encode perhaps individually, right? But then there's this big long set that's just duplicated. So what I might be able to do is put a number first. For example, right before here, if I've got these, I'm going to stop it right here and say I've got these 7, right? 1, 2, 3, 4, 5, 6, 7. If I first encoded a 7 and then said A, B, C, E, G, H, A, right? Well, I've expanded my message by 1. I've inserted 1 symbol here, all right, so it got a little bit bigger. But then what I could do is I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 repeated B's. I could just say 9 and then a B, right? And so if you look at what happens here, all I would need to do now is encode some way of saying the 7 is how many things I have in a row that I care about, right? And the 9 is the thing that encodes that the thing that comes after it is just duplicated a bunch of times instead of looking for new pieces of information that come after it. And oftentimes the way that this works in RLE is says, well, I won't even bother spending any extra information to communicate that. All I'll say is that we just go in pairs. I send a number of literals, as they're called, basically things that I'm going to encode directly, and then a run. Literals, run. Literals, run. So I just do how many pieces of new information do I have? I put them in there. How many pieces of replicated information do I have? I put them in there, right? And then the next one, it would be a literal count again. And if I didn't have a run, and I was at the maximum size that I could fit in here, like let's say these are bytes, so maybe the maximum number of literals I could have is 255. For the run, I just encode a 0. And then it would be like, oh, OK, there's nothing. There are no repeated values here. And then the next thing would be another count of literals, right? So hopefully you can see how that run length encoding is very, very simple. It's basically just a number of how many new pieces of information I have, then a number of how many replications I want to do of the next byte, right? So it's just like new bytes and then the bytes, run count and then the byte to repeat, new bytes and the bytes, run count and the run to repeat, right? So hopefully that makes a fair bit of sense, right? It's very, very simple encoding. And, for those of you who ever were back in the day, if you ever heard of like the old school formats, like maybe you're like me, you grew up, you had an Amiga in the household, the Amiga computer. Electronic Arts, I believe, is the company who introduced this format. It was called the Interchange File Format, or IFF. And it had the interleave bitmap format was a sub-format of it that could be put in there. IFF was kind of a container format that can hold multiple formats. It was RIFF related. I don't remember what RIF even stands for, but RIF chunks are a standard thing, and I'm sorry, I can't remember what it stands for. But anyway, this file format actually had run length encoding in it. So if you ever remember how bitmaps were stored on the Amiga, I believe RLE was in there. Again, back in the day. I believe there's also like maybe PCX. I'm sorry, my memory is kind of fading here, but there's some old school formats that graphics formats that use this. It's not really something that's used very commonly anymore, but it was not so uncommon back in the day. And why was it not so uncommon? Well, if you think about it, it's really, really simple, right? This can be coded in a few lines of code. It's just read 1 byte, copy the number of bytes from the input stream to the output stream that you just read, read 1 byte and a replication byte, and just do a for loop to output that byte that many times, right? That's it. So it's very, very, very simple. It takes almost no code and can run very quickly, right? So the point that I want to make about RLE versus LZ here that came up in the pre-stream is LZ compression is a sort of a much more heavy-duty form of compression, you might say. And why do I say that? Because at the outset, I sort of said, well, compression is a no-win scenario, right? It's like it's just about selecting certain sets of information that you can encode, and you can't really ever make something that makes everything smaller. So why am I saying that this is like more heavyweight? What does that even mean? Certainly, it should just be that no matter what encoding you choose, some things are much better than others, and blah 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 blah. Right? Well, all I really mean to say by this is a much more commonly applied compression technique. So if nothing else, we could probably say that our experience so far has shown that LZ as a technique tends to encode human-style messages much more interestingly than RLE does in terms of getting good compression out of it. So, even though compression is a zero-sum game, it doesn't mean there aren't better and worse compressors for the kind of information that we typically care about. And LZ compression is something that's used in basically everything that you use today. Whether it's 7-zip or PKZip or any of the sort of zip-based utilities that you use, or in a PNG file, for example, anywhere that you're doing lossless encoding, you're going to see a lot of LZ related techniques. And it's been around for a very long time. It's been around since the 70s. And it's just something that hasn't really been beaten. I guess for whatever reason, it really hits a sweet spot in terms of efficiency of coding versus ability to actually get compression out of the types of messages humans typically send or care about storing. So LZ is a very, very popular compression format. But maybe it's a little bit more daunting to understand than RLE or something like this, or maybe you think that it's it's kind of a little out there. And I just wanted to make the point because we were talking about in the pre-stream, that LZ and RLE are almost identical. LZ is just a tiny, tiny little bit more than RLE. So if you feel comfortable programming run length encoding, you also, trust me, will feel very comfortable programming LZ, which stands for Lempel-Zib. It's named after the people. It's not like run length encoding where it's named after kind of what it does. So this is very easy, especially the decoder. Now the encoders are a little more complicated. Not that much more complicated, because you don't have to take it to the nth degree. One of the things about encoding that I'll talk about in a second is that the reason that an RLE encoder is more straightforward than an LZ encoder, although one of the reasons is you'll see in a second is this because there's a little more bookkeeping to do just to make a Lempel-Zib encoder. than there is RLE. But with a lempel-ziv encoder, there are choices about what's the best thing to encode. So there's options. There's not just one right way to do a lempel-ziv encode in terms of when the code looks at it. Whereas with RLE, that's not true. RLE, there's only one way to encode the data for any given scheme, so it's just instant, pretty much how it works. I guess, well, maybe that's not exactly true. I mean, I could see for some RLE schemes like the one I laid out here, maybe there are a couple choices you could make. So, maybe I wouldn't even go that far. I guess maybe the better way to say it would be, with something like lempel-ziv, your encoder could get perhaps significantly more compression by making different choices oftentimes, whereas with RLE, maybe that's not the case as often. So I don't know, maybe let's soften that a little bit. But either way, you can ignore all that. All I really wanted to show was about the decompression and how simple LZ really is, so that you can feel like maybe it's a little bit more accessible to you than it would be. So again, if you feel comfortable with RLE, you should feel very comfortable with LZ, and here's why. So all an LZ encoder does is basically exactly the same thing that we talked about. But instead of encoding runs, the run part, right? So the literal part is almost exactly the same in LZ. There's really no difference. There's going to be some way in a lempel-ziv scheme to encode the fact that we've got a bunch of new bytes coming, and then we encode the bytes. That part stays basically the same. The part that changes is the run part. Instead of talking about runs in a generic sense, right, where we're saying, oh, hey, by the way, when I say something's a run, I'm just going to give you a byte and you replicate that byte, right? So rather than encoding runs that way, instead what I'm going to say is, in addition to just a count, I'm also going to give you an offset, okay? And the offset is going to be some look back into what I've already sent you. And then you're going to take that many, whatever I said the run was, you're going to copy that many things from the previous information. So for example, if I had something like A, B, C, D, G, H, I, A, B, G, H, A, B, C, D, right? And one way that I might encode this is say, well, OK, if my encoder notices that we have an ABCD and an ABCD in both places, right? Then it might choose to, and there's, you can notice this AB here. I'll talk about that in a second, and these GHs, right? We'll talk about those in a second. But I see these ABCDs here in the encoder, and I say, oh, OK. So maybe I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe I encode my 11, and then I encode this, right? And those are all new bytes. So these are literals, right? Then I look at the ABCD and I say, oh, back here, I already sent an ABCD. So instead, what I'll say is just, oh, go back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bytes, right? And then copy 4 bytes. So, the run length is 4, the distance is 11, and that's all I needed to encode. So instead of having to write 4 things into the input stream, I only had to write 2, right? OK. So hopefully that makes some sense. And again, there's some subtlety here, because when you encode things like this, you still have the problem of, how do I encode what thing I'm doing? Like, if I say that I have an 11 here or a 4, how do I know what that means? And like one answer, like it was in the RLE case, is to just say that they're alternating, so the decompressor always knows it does one then the other, one then the other, one then the other. It doesn't have to spare any extra bits. Other things might have individual bits on there that are like codes that say, oh, you do this or you do that. So you can trade off information in various ways. That's, again, getting into sort of the minutia compression, which I wasn't sort of going to try to do. But I just want to point that out. So if you feel comfortable coding this, you probably feel comfortable coding this. I mean, how simple is this decompressor? I just read a number, right? I then copy that number of bytes. Then I read a number and a second number. I use the second number to figure out how many bytes to go backwards. Like I just look my pointer backwards that many bytes, and then I copy this many bytes to the input stream, right? OK. So again, hopefully anyone watching who's at all comfortable with anything we do in Handmade Hero is going to be very comfortable with that because, I mean, how simple is that, right? Very, very simple. It's certainly only the tiniest bit different than this. So it's very, very basic to write an LZ decoder in that sense, right? So the thing that I wanted to show you in addition, this was the part that originally made me want to go say this, because I, first of all, wanted to say, hey, Miblo, if you feel comfortable with RLE, you probably would feel very comfortable with this. And I think, hopefully I'm right. But here's the really cool part about LZ. And I rarely see this sort of thing mentioned, probably because it's so, by the time someone becomes a compression expert, this is so not interesting to them that they probably don't think it's as cool as like I think it is. I recently implemented my first actual like compressor that'll probably ship in something, because I never do compression. But for 1935, for the game that I'm working on now, I did my own compressor because I basically wanted almost, essentially all the code in the game to be code that I wrote. And so I had to write a compressor for it, and I kind of had to learn like roughly how to do some of these things. And I thought this was just so cool. When you have an LZ compressor, based on what I just told you at first, and again, so I'm assuming that you're like me. Those of you out there who are compression experts already know this, but if you're like me and have kind of saw this stuff for the first time, right, going through it, you're like, oh, okay. Well, if I come from an RLE compressor and I go to LZ compressor, that allows me to like exploit these patterns really cleanly, but I've lost the ability to do big runs of the same thing, right? Because now, naively, you might think, well, now if I wanted to encode a big long run of these Bs like this, it's like, well, how do I do it? Well, I guess I encode maybe 4 Bs or something, or some reasonable number of them, and then I encode a replication that says to replicate those 4 Bs, and then, I encode a replication that says replicate those 8 Bs or something, and you build up by doing squared every time. Like I put 2 Bs in, I replicate the 2 Bs, then I replicate the 4 Bs, and I replicate 8 Bs, right, and build it up. And it seems like I'm taking a lot more space to encode just a big long run of like, 100 Bs or something like this. But the reality is, as long as your LZ decoder is operating sort of just in a buffer, and you're just kind of writing to the buffer, you can actually get an RLE encoding basically for free in your LZ encoder because of the fact that there is no reason you can't replicate symbols in the middle of the same run. Now let me show you how this works, because this is the thing that I thought was so cool. I was like, oh, wait. When I realized this, I'm kind of like working on it, and I'm like, oh, cool, right? So what happens here is, let's say that I have that exact scenario that I'm talking about. So I've got A, B, C, D, 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 and it just goes on forever, right? So there's just an infinity of Ds that come after this. And I want to encode them all. How do I do it, right? And so like I said, the naive way to do this would be to say, oh, OK, maybe I put out my first literal, and I just try to get that far in, right? So I say like, oh, my first one was 1, 2, 3, 4, 5, 6, 7. Right? So I say, OK, 7, and then I encode my A, B, C, D, 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 right? Then I go, well, I'll replicate. I go back 4, right? So I say my distance to look back is 4 or something like this. And then my replication is 4, right? So I just take this, and then that'll output it, D, 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 right? And then I'm saying like, OK, the next thing I want to do is replicate this whole thing. So I would do like, oh, my look back is 8, and I want to replicate 8, and then I've got 16, and there I go, right? And you can see why I'm saying that looks really bad, because like, hey, that's so much worse. The RLE version of this would have just said, oh, I've got, however many I've got, 100, and then D. And that's all I would have had to have sent, and there's all the Ds, right? So it looks like this is way worse. But what you have to remember is that if the decoder is just writing it into a buffer, you can actually just do the RLE part for free. When I get here, I go, oh, I've got all of these Ds that come here. So then all I do is say, well, OK, encode for A, B, C, D, right? Now I want to replicate this D. Well, all I have to do is encode the 1, which basically says look backwards 1 for the start of my run, which is here. And then I just say how many I want, right? I want 99 more Ds, right? And look what happens. the decoder goes, oh, okay, take a D from the input stream, right? Because it's starting here and it's going to copy. And where does it write it? Well, it writes it right here because that's the output point. Now it goes forward to try and continue reading the run. And it looks and finds the D that it just wrote. Like the decoder just wrote the D, but it's there in the buffer, right? So then it reads that D and goes, okay, and writes it here, right? So essentially, an LZ decoder can self-replicate what it just wrote, which means that it is no less efficient, really, to encode those runs. It's slightly less efficient because, like I said, you have to encode the lookback, potentially. So it might not be quite as efficient, in terms of 100% of the bits, but in terms of generically speaking, how hard is it to encode a run? It's actually really easy to encode a run because it just self-replicates out. And what's more important is that unlike RLE, which has to talk about a specific pattern potentially, like if I wanted to look at my RLE encoder, well, if I wanted to encode a run of something more complicated than just one symbol, let's say I wanted to encode BD, 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 or something like this, I would need an additional symbol in here. In addition to the run count, I'd need how long the sub-piece of the run was, so that the decoder would know how many of these symbols to pick out and replicate, right? Not so with LZ. With LZ, the look-back count is basically the same as the duplication count, right? It's if I wanted to replicate CD many times, I just encode a 2 here. And then I would have 99 copies of CD because it would write a C here, a D here, right? And because it's like it's reading from here, it moves to here, reads from here, and it wrote here and here. Then it moves to here and reads C and D again. And then it just keeps self-replicating its own pattern and on and on and on, right? So essentially, an LZ decoder has a run length encoder built into it for free. And free is not really possibly the correct term here, but almost free. So that's just a really, really cool aspect of LZ. And it kind of just shows why it's such an interesting algorithm, too. Like it's got so much versatility there because not only can it do that nice grabbing patterns that I've seen before, but it can also go ahead and duplicate, just like an RLE is, in big, long runs. What's more is that it only takes 2 steps to do a duplication from anywhere in the stream. Because if you think about it, what was the requirement for me being able to dupe here? Well, the requirement for me being able to dupe here was that I am able to put the thing I want to dupe at the end of the stream, right? Because it needs to be A, B, C, D, right? And if I want to do is like C, D, C, D, C, D, right? Well, if I wanted to do this duplication, the requirement is just that I have to send it, and then the last thing in the buffer, right, has to be the thing that I want to dupe. Because I'm going to encode a lookback, right, and then I'm going to encode the duplication count, whatever it is, and it's going to replicate, replicate, replicate. I couldn't encode a bigger lookback. Like if I encoded 4 here, because I wanted to replicate AB, like, I'm just to give you an example, let's say it's AB, CD, AB, AB, AB. I couldn't do this one, and the reason that I couldn't do this one is because if I looked back to here, and I'm right here, if I look back to here and start copying, I'm going to have to copy the CD. So it's going, because if I say 99 and my look back is 4, it's going to go like A, B, C, D. When it reads the AB, yeah, it'll put the AB here. It'll write the A, it'll write the B. But then it'll write a C and a D into here before it gets to the AB again. Right? So I'll end up with A, B, C, D, A, B, C, D, A, B, C, D, E. So the LZ can rep that last thing in the buffer, but it can't rep an arbitrary pullout. But with 2 steps, it can. Because obviously, at any point in LZ, if I've got some big long run here, let's say this is the thing that I want to do. This is going to replicate many, many times. So I've got A, B, C, D, E, F, G, H. It's a big, long string, however long it is. And then I've got, I, J, K, here. And then I've got the dupe. A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, H, dot, 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 on and on and on. So I encode this big, long thing as a literal, and then I get to here, and I'm like, oh, I want to do like an infinite dupe, basically. Like maybe this replicates many 99 times, like the other one does or whatever, or 100 times. I want to sort of grab this part and I want to replicate it, but I can't do that because it's not at the end of the buffer. Well, that's OK. It only takes me 2 steps, right? I just encode the look back here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So I say, oh, the look back is 11. And then I say 1, 2, 3, 4, 5, 6, 7, 8 is the thing to copy, right? So I go ahead and put that forwards. That will write the first one in. And then I just encode immediately after that my look back is just another 8, and then my replication count, which is 8 times 100, however many I wanted there. It's 800 or something like that, right? Now, granted, that's greater than 255, so I'd probably have to do this in pieces. But you can see how I can just move it to the end. And by the way, I guess I kind of misspoke here. When I said the replication count of 99, what I really mean is 99 times 2, right? I mean times the length of the thing that I'm replicating, right? So that was a typo there, or a mental slip. So hopefully you can kind of see how it's really very versatile, because the encoder can do lots of things, right? The encoder can encode just chunks that it wants to replicate, but it can also move chunks to the front and then dupe them, or just dupe the last thing that it saw. For the entire size of the rep count, it can do, right? So it kind of gets you just a lot of versatility there, and that's one of the reasons why LZ is such a popular algorithm. It's because it's very, very versatile and gets a lot of bang for the buck there. Again, if you assume you're sending a lot of signal, if you assume that the information you're dealing with has a lot of self-replication or self-regularity to it, which again is generally true of the sorts of things that humans tend to do. Like, we tend to have a lot of regularity in our information, hence LZ works very well. If we were a species whose information typically included a lot of white noise, this would be useless, because the data would look all completely random and there wouldn't be pieces that you want to copy, and the kinds of techniques we would use to compress things like white noise would be very different, right? It wouldn't be this kind of thing where, our information, we tend to value information that's highly ordered. That's the kind of information that humans traffic in, probably for good reasons, but I won't try to suss out any philosophical underpinnings there. I'll simply say that, we tend to have highly ordered data, and so things that can exploit the order in the data like that tend to be very useful for human-style information, and that is exactly what we care about when we are doing compression for things like games that are made up entirely of human-created assets. There you go. So that's LZ. Now, if you want to write an LZ decompressor, hopefully it's just immediately obvious how to do so from what I've just said, right? There's no mystery to it. It's literally like read a number of bytes to output those bytes, read a number of bytes to replicate, plus a number that tells you where to look back into the stream, and do the replication. Now, one of the things that I baked into here that I didn't really mention is, well, why is it encoded that way? Because you could encode it in a lot of different ways, right? And the reason that typically LZ schemes tend to be about looking backwards from where you are is because most of the time, again, this is sort of like a prejudgment, right, if you will. I hate to use the term prejudice because that sounds negative. We're not really trying to be negative about it. It's just that's what it tends to be. It's a pre-made sort of idea about how this data is going to look that we don't really know that it's going to be true, but most of the time we hope that it is. We're going to pre-say that we expect most of the time when we see patterns, those patterns are more localized than globalized. So if I have some very long message, and I've got, maybe this is a novel or something, and I've got all these pages of my novel, right? And here's page 1 and page 2 and page 3 and page 4, and then I'm up to page like 927 because, maybe this is by Mishner, so it's really, really long, and it just goes on forever. Well, you could imagine I'm trying to encode these things. Again, remember, everything that you encode has a cost. If I want to encode the distance to look back, for example, or where I'm going, let's make it more generic. If I'm going to encode the location of the data that I'm trying to grab with some number of bits, well, however many bits I choose is going to affect how good of a compression I get in various ways. If I say that I'm going to use 8 bits to encode where to look, well, that means that I can only specify 255 different positions to look in, right? If I said that I was going to use 32 bits, well, now I can do 4 gigabytes worth of location. But every time I encode one, it's 4 times larger than this to encode that position, right? So I'm losing compression by gaining the ability to perhaps get some more compression by being more specific about where to look. So there's this kind of trade-off there about how many bits I'm using, right? This gets a little bit more complicated when you talk about backends and entropy encoding. And I'll kind of leave that. I'll say a final word about that if I remember afterwards. But so you have to remember that in a lot of encoders, there's a step after LZ, which is like Huffman encoding, arithmetic encoding, Rand's encoding, these sorts of things, that is designed to more optimally deal with the bit count. But the point still stands that however many bits you actually use, it makes a difference, even if you're using one of those backends, because all those backends do, for lack of a better term, is they make it so that you're only paying for bits you actually use and not for bits you don't use. So for example, this 32 bits, it may be that the high 4 bits are very rarely used. Once in a while they are, but very rarely. Instead of paying for them every time, you pay proportional to how often you use them, right? That is what those other sort of backends help you do. So it's not as clean as saying it's 4 times bigger to like do this encoding or something like that. There's more to it than that. That's all I was going to. But for purposes of thinking about it, it's not really that different than saying this. Let's assume that you're actually using the bits you're allocating. It is 4 times bigger, right? Okay. So this has a cost there. So it has a cost to say that I'm going to allow my compressor to encode the signal in a way, or the information rather, by reaching further back, or by picking a particular position in the stream. So if we were to say that we were going to use 32 bits, it might be fine to use an absolute position. Like we could just start at the beginning and say where the thing was that we're replicating, right? But that would require that we have enough bits to sort of encompass the whole message, because otherwise when we start getting, eventually we'd only have the first few pages, right? So let's say that's what we did, and we said 8 bits. Well, 8 bits is only going to get us maybe the first page of our novel. That would mean that if it was an absolute encoding scheme, right, where we just said we start at the first character of the entire stream we've done, and we just can go 255 bytes into it, that's only like the first page of our novel. It means that the only signal we can reference to duplicate, the only pieces of information we can duplicate, are from that first page. Well, if all of the words that we tend to use frequently all occurred on the first page, great. But what's the chances of that? Probably there are new characters who were introduced into the thing, new location names, new manners of speaking, depending on which chapter. Maybe some's in first person, some's in third person. You know how a novel is, right? So it doesn't make a lot of sense to encode the 927th page of our book using the same information as encoded the first page of our book. And that's why encoders like this tend to use relative positioning, because the chances of finding a match for where we're at right now tend to be much higher if we're talking about the most recently seen 255 characters, rather than talking about the very first 255 characters that we may have encountered. So that's why typically, no matter how many bits you tend to allocate in an LZ scheme, you oftentimes want to make them relative to the output position, because that allows you to more likely capture the information that's going to be replicated. Because again, one of the assumptions that we make about this data that we're trying to compress, based on just the way humans tend to do it and the kinds of things that we tend to value in terms of information, the types of things we tend to produce, usually when we say something or do something or make a color in a picture, the things nearby tend to be more similar than the things further apart. It doesn't have to be true, and that's why you can always construct things where it would have been better if you did it the other way. But for the most part, it tends to be this way, right? So hopefully that makes some sense. Okay. So I'll say 2 more things about this. LZ encoding. So LZ decoder, like I said, super simple, right? It's just a question of coming up with exactly how you want those bytes to work. But if you just want to do it as a programming exercise, you don't maybe have to worry so much about are you getting good compression. You can just sort of think about it as let me just make something that works. And like I said, we've talked about a very simple scheme that could work. Read a number of bytes to new bytes that are going to come in the stream. So you write the number of new bytes, then the bytes, and then you just write a number of bytes you want to copy and the look back amount, right? And then one more number, you go back to the beginning, one more number, that's how many new bytes are coming, the new bytes, right? And just go on forever. It's exactly like an RLE encoder, but now it's an LZ encoder, decoder at that point, right? Very, very, very simple. Hopefully everyone who's watching would feel very comfortable doing that. If you made it this far in Handmade Hero, that's not very hard at all, right? LZ encoding, on the other hand, it's a little bit harder, and even just to do even a basic one is a little bit harder than something like an RLE encoder, which is very straightforward. An RLE encoder basically just involves looking ahead a few symbols to see, am I replicating something? If I am, encode it that way, otherwise don't. That's really all you have to do for an RLE encoder, right? If I just want something that captures this idea, right? The only thing the RLE encoder, the basic kind of RLE encoder, can do is just capture this run. That's all it can do. So all you do is you just look ahead one symbol at a time and say, is it the same as the symbol I'm on? If it's not, I just keep stacking up my literals. If it is the same, then I just keep a little count of how many there are. When I get to the end of that, when I see the first differing symbol, which would be here, right? I go, how many did I have? I've got 5. OK, encoder run. 5 in the number, right? So the encoder is very easy. It's just all it is just looking ahead a few symbols to see how long any individual run is. And when you see it, you output it, right? So very, very simple encoder, not a lot of decision making to have. There are places you could imagine making some decisions about that, but they're very, very simplistic. There's not a lot of complexity there in terms of getting the compression you would expect to get out of RLE. There's just not a lot there. But for LZ encoding, it's more difficult. The reason it's more difficult is because now you've got this whole back catalog, right? Let's say we are doing byte-based. So let's say we have an 8-bit look back, right? That's 255 positions in the output stream starting from where I am right now that could be selected as a place to copy from. And now I have to make a decision about those 255 locations, right? I have to have an opinion. Which of those 255 should I encode, if at all? Because I also could just encode a literal. I could say, here's new bytes, right? So if we think about this, the question is, how do I figure out which of those to do? Well, the brute force method, right, you can think about, it's actually pretty easy. If I literally wanted to make an incredibly slow LZ encoder, I could just say, all right, for all 255, right, I just literally from 0 to 255, right? For each of those, do a while matches, run ++, and keep the best, right? So you can imagine what this kind of thing does, right? It's like the brute force method, which is very, very slow. It's like, all right, I'm here in the input stream. Go all the way back to however far back I can go. If it's 255 symbols is my maximum, then go back all the way to there, right? Start there. And now I know I've got some symbols here, right? X, Y, Z, W, whatever they are, right? My new symbols are here. And maybe there is an actual run. So maybe the run is C, D, 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 right? So maybe there is the new symbols that are coming do match something. They match right there, right? All right. So go back all the way to the beginning. See from this symbol, how many symbols in the input coming next do I match? Well, this is an A and that's a C, so none is the answer, right? Then this is this part of the for I loop here. I go to B, right? B, OK, let's see how many matches I get. This is this part of the loop here, while matches. OK, B and C, none, right? So again, nothing matches. All right. I come to the C and I say, all right, the C matches. Oh, cool. Do the, increment this run count. I go D, D, D. All right, so I actually got all the way here. And maybe this is an E, so this doesn't match. Oh, so I got a 4. Well, that's the best run I've seen so far. So save this location as my best run so far. I keep going, right? I check this location, right? I don't start here. I still check this location because maybe the run counts or whatever. And again, because this is brute force, you could actually know that that wasn't true by doing some other things, but that's beside the point. So I go through all of these, and I do all of that, and I find my best run is 4, and it's here, so that's what I encode, right? So that's a brute force, very simple LZ encoder. Now you can imagine that this gets pretty bad, especially if you imagine, let's say you wanted to do a 16-bit look back. Well, now you've got 6, 5, 5, 3, 5 different positions to look at. This becomes, sort of this very bad n squared thing. Maybe my run count is 16-bit as well. Now I've got this much work to do potentially to do my checking. It's not that bad because they won't all match, but it's pretty bad. So you can imagine this getting extremely slow. So typically what people do here instead of this is they try to keep like a hash table as the window slides through of like locations and what the first 3 symbols of that location, let's say, are. So you do a hash on BCD, on DDD, and so on, and you have entries into a hash table so that when you see CDD, you only look up into the hash table and you only consider positions that started with CDD, right? To keep your sort of match checking down. And typically the other things you have to do is, you'll oftentimes get runs of just a bunch of things. Like if we had that thing where we've got all these DDDDDDDDDs, well, each one of these is going to hash, right? Each of these DDDs is going to hash into the same slot, and you're going to end up with this big old hash collision, which is not helping you cut it down at all, right? So the other thing you need to do oftentimes is keep sort of information about overlapping runs. So you're like, okay, I know that this DDD, this run, and this run, right? I know that if I started, if I checked this run and I got into this run somehow, then I don't need to check this run at all. Because there's no way that once a run like overlaps, I know that I would have kept going at that point if I could have, and I didn't, so starting here is not going to help me necessarily, or whatever, right? You can imagine like encompassing a run at that point means that you only needed to check one of those runs. If that makes sense. So yeah, anyway. I'm not stating that very well. What I'm trying to say here is, if you got into a run at the same place from 2 different locations, you can stop checking the run because you've already gone as far as you were going to go, and the other run would have been longer because it started earlier, is I guess what I'm saying. So yeah, there you go. All right. So my final note on this is just talking about the entropy encoding backend situation, right? LZ is basically a technique that says, let me use sort of these pointers back into, sort of references, relative references back into the data that I've already seen as a way of pulling out common things that occur that we've already seen. So that, very straightforward, hopefully, and you can kind of see how that works now that I've gone over it. But like I said, a lot of compressors don't just use LZ. Now, it's possible that just using LZ is your best bet. That can be true, right? There's certainly a class of classes of information where just using LZ directly is the best thing to do. And off you go. But it's also possible that using LZ alone is not as efficient as using LZ with something called an entropy encoder on the back end. And what this is these are techniques, like I was saying before, like Huffman, arithmetic, and RANS or TANS, things like these. And what these are techniques that allow you to take a look at the actual information you're encoding per symbol. Remember, like these symbols here, we've kind of broken it up. Maybe that's like bytes for the symbol or whatever, or maybe it's an 8-bit symbol per symbol or 16 bits per symbol. Right? Taking a look at those and saying, okay, after I do my LZ compression, maybe my output, my result, right? So my result, again, keep in mind, my result is the actual encoding of like, 4 literals, and here they are, then a look back of 2 and a rep count of 8, these sorts of things. So 4, ABCD, 2, 8, then some symbol, blah, blah, blah. That's my actual thing that I'm talking about when I say my result. not the message I actually encoded or the information I encoded, not that, but its compressed representation. So the post LZ, it's run through the LZ encoder and is now whatever that bit pattern is. So after I do that, right, after I encode my post LZ encoding, take a look at that and say, well, I know that each one of the things in here is 8 bits, or maybe some are 8 bits and some are 16 bits, whatever. However it's broken up, I know that it's broken up into these chunks that I understand. It's got the literal count and then the literals encoded, then it's got the rep count and the distance count. I know what it looks like, and I know there are these chunks, and I know how many bits I allocated to each one. But here's the thing. It may be that if you look at these, they are not using all of the bits equally for the same purposes and the same ways, right? It may be that if I looked at a histogram, let's say, right, so like took a chart and I said, what's the frequency of seeing a particular value, right? And here's all my values, right? So remember, in 8 bits, let's say I have 8 bits, I could have 255 different values, right? And then the frequency is like, okay, how long is the message? Right? Maybe the message is 50 bytes long, right? So that means the maximum frequency I could see is 50. If I just saw the same thing 50 times, if I saw the same value 50 times, that's the most it could be. And I have 255 values. Here's my 0, right? And here's 255, and here's 128. Those are the values that could have been encoding in a byte, right? I could look at this, and if it's just flat, right, which it can't be. Let's, you know what, I should make this at least more. Let's say that it's 512 or something, right? Something like that. So, right? If every symbol appeared exactly twice, then it would just be a flat histogram that looks like this, right? Every symbol is equally likely to occur, okay? In that case, LZ was great. LZ, we're done, right? It outputted a stream that has completely uniform probability that every type of value in a byte was equally represented. But what if it's more lumpy, to borrow a phrase from Jeff Roberts that he used at Handmade Con? What if it's more lumpy? What if 0, for some reason, appeared many more times than everything else? So maybe 0 and let's say maybe 0 and maybe something over here appeared a couple times, but everything else was like very, very low, and there were these 2 spikes. So I'm much, much more likely to encode a 0 for some reason because of the nature of the data, let's say, and I was much, much more likely to encode a 97 for some reason, right? Well, now, if you think about it, I'm not really using all 8 bits every time I output a byte, because I'm much more likely to be talking about 0 and 97, which would only require 2 values. So it would only take me 1 bit to encode a message that was all zeros or 97s. But I'm writing 8 bits every time. And yeah, I do still need 8 bits of data because I do occasionally throw in a 4. And I do occasionally throw in a 237, right? So it's not that I could have actually used 1 bit, but it's that most of the time I could have used 1 bit, right? Well, that's where these entropy encoders come in. These entropy encoders are ways of saying, oh, what if we actually just used bits to encode the data, and we used a number of bits for each symbol that was proportional to how many times it actually shows up? How might we do this? Well, let's take a simple example from Huffman, because arithmetic and RANDs are much more complicated to understand. But they all do the same thing. They just do it to better efficacy. Huffman, it gets less efficiency. It's larger. Huffman is the best you can do at a bit granularity, but arithmetic and RANDs allow you to do sub-bit granularity. So like arithmetic and RANDs allow you to do stuff like use 1.5 bits to encode things. I know it sounds like magic. It's not. I'd encourage you to go read about it if you care about it. But again, that's why these are a lot more complicated to understand, is because it seems like a little bit of magic. But something like Huffman's very easy to understand. Let's say that we wanted to do this exact thing that we talked about. I want 0 and 97 to be very easy to encode, but I want all the rest of the values to take more space because they almost never occur, right? So all I have to do is say, like, all right, let's just say that we read the input stream 1 bit at a time instead of 1 byte at a time. So I'm going to grab a byte out of the input stream, and then I'm literally going to go through the bits in it one by one to actually make sense of it, rather than saying I always operate on 1 byte, right? So what do? Well, I read the first bit in the input stream, OK? So here's the first bit. Here's bit 0. And I say, well, is it a 0 or is it a 1? Which one's it going to be, right? And whichever one it's going to be, I'm going to make a decision. If it's a 0, I'm going to say, oh, OK. If it's a 0, then I know that I'm in my high frequency thing. Maybe I'm in the 512 versus 97 thing, where they're both really highly likely. So then, when I get, and let me draw this maybe a little bit differently. Let me do it this way. OK. Then I'm at bit 1 here, and I'm at bit 1 here, right? So I read a 0, and then I say, OK, read the next bit if I'm at a 0. And whatever that bit is, right, if that bit's a 0, I'm going to output a 0. If that bit is a 1, I'm going to output a 97, OK? Now it's taken me exactly 2 bits, right, to encode a 0 or a 97. If the bit is a 1, then, that first bit was a 1, then I have the rest of my tree, and maybe that rest of my tree, if these really were uniform probability, the rest of that tree is just, OK, put 7 bits after it, or 8 bits after it to say what the actual value was, right? Does that make sense? So basically you can think about, and this is like a Huffman-style way to encode things. So basically if you think about it, all this is using bit encoding to say, well, you know what? Almost always what I encode is one of these 2 values. Let's make it only 2 bits to encode one of those values. And then I'll make it so that everything else takes 9 bits, right? A 1 bit followed by the actual 8 bits of data. But if it's a 0 bit instead, then I'm just shorthand for 0 and 97. Now what I've done, if I really did have this scenario where almost everything is either a 0 or a 97, now what I've done is I've gone from a message that used to take 8 bits per symbol. So if it was 512 long, it's 512 times 1 byte per symbol, right? Or we'll use bits, times 8 bits per symbol. So I've gone from a message that took 8 times 512 bytes to 512 bits to one that takes 512 times 2 bits most of the time, right? Because there's only a couple times when I actually need to encode these other guys, right? So at that point, it's like, hey, great. This is a 1024-bit message now, roughly, whereas this one right here was what? A 4096-bit message. That's a great savings. I've just saved, it's 4 times smaller, right? So that's all these things do. They basically take a histogram of the data, a frequency count of the data, and they try to allocate the bits of the output so that it matches that histogram. And what you can sort of see here, to further understand why these other 2, and there's probably a lot more than these. Again, I'm not a compression person, so I can't tell you all the ways in which you might back-end encode something. There's certainly probably a lot more than I'm listing here, but again, I'm not familiar with that branch of programming. So if you take a look at these, right, what you see there is it's like, OK, Huffman, arithmetic, rands, and tans, for example. Huffman, because it looks like one of these, there's tons of ways you might organize how your Huffman trees were working and all these other sorts of trade-offs. Who knows? Again, not a compression expert, couldn't talk about them intelligently. But if you're organizing it on a bit tree here where you say, like, OK, there's a bit that's a 1 or a 0, and I go in a direction based on that down the tree, and the tree is designed to be balanced out so that the tree is shortest where the symbols are most frequent and longest where they're not, that's Huffman. It has a quantization problem, right? It has the problem that whatever these frequencies were, they probably weren't binary frequencies, because that's what this tree will give me. A path to a symbol on Huffman is going to be an integer number of steps. It's 2 bits to get down to here. It's 2 bits to get down to here. Whatever this is down here is 4 bits to get to, or whatever, right? So I can only encode integer multiple frequencies exactly in my Huffman tree. So if I actually have something where which almost all histograms will not fall into that category. Most histograms, if I say, well, the total length is 512, and the number of times I saw, this particular symbol is 17, well, that's not going to divide out to anything that approaches an integer, right? That is not an integer. But that's how many bits I wanted, that's how, or not how many bits, that's what proportion of the output bits I wanted that symbol to take, right? That is not going to be encodable in an integer step tree like this. And so what these other techniques do is they devise more clever ways of encoding that allow you to know, oh, okay, I want to produce a fractional number of bits to encode this thing. And again, I really am not comfortable enough with the math at this point to try and offer an explanation. Huffman is very easy for a programmer to understand, I would say. Ooh, did I just lose? I just lost smoothing there. That's interesting. Is that because there's something else? That was like right when it switched, this thing came up, I lost smoothing. I wonder if that's information for Sergio, because he was wondering why he lost smoothing, and it seems like that's a pretty interesting coincidence. Anyway, doesn't matter. So point being, that is what these sort of additional techniques do, and basically like arithmetic versus rands or tans or whatever. The reason that people, as far as I know, Huffman is never what you actually want to use in terms of size. I could be wrong about this. So please take it with a very big grain of salt, because I'm not a compression person. But my understanding is that Huffman, for example, is like a very inefficient way to store the data compared to arithmetic, for example. It's not like there's a trade-off, it's just worse. And very inefficient is probably wrong. It is inefficient, right, compared to arithmetic. Because arithmetic can match the histogram exactly, whereas Huffman can only approximate it by an integer match of the histogram, right? So that's my understanding of it, is that you would never use a Huffman encoder instead of an arithmetic encoder if what you cared about was space. My understanding is arithmetic is always better. That's just my understanding. I don't know if that's true. Meaning, it's not like, oh, Huffman works better for these signals and arithmetic works better for these signals. I thought that arithmetic was always preferable. But arithmetic was a lot slower. It involves integer divides or crazy table lookups and all these sorts of things. And supposedly, again, the people I know who do compression, what I glean from their discussions on it, and again, please take it with a grain of salt, or even a cube of salt, like a salt lick the size of the kind you give to a horse, is that Huffman encoders are encoders where you're doing them because it's faster. You can implement them more quickly than you can arithmetic encoders, because arithmetic encoders involve things like integer divides or things like this, whereas Huffman encoders do not, and they can be done directly with bit manipulation that's much faster. That's my understanding of why you see Huffman encoders, because they are the very fastest back-end encoders that still do a reasonable job of histogram compression. But if you had unlimited time, you would not use this, was my understanding. There's no size win for it. It's always a loss in terms of size, or it's always equivalent to arithmetic or worse. But these RANS, TANS encoders are like a new thing. The ANS thing was something that was, I guess, invented by or discovered recently in terms of the mathematics behind it. And I don't know if the folks at RAD were the first people to actually figure out why it was useful. I think they might have been, actually. I think Charles may have been the first person. I don't know. I don't want to accidentally give credit to the wrong people or something like this, but I think that's actually what happened. You should, I don't know, maybe check the history books for this. I'm not sure if anyone keeps history books on this, but it turns out that by using the mathematics of these ANS things, which I don't really understand at this point, so I can't give you any kind of insight into how they actually work. But you could read Fabian. Fabian posted some articles on it, and you could read some of his write-ups if you're interested. I don't know if Charles posted, probably on his blog he has posted some too. But basically, the way that these things work is they get arithmetic compression. They get fractional bit precision on the histogram, just like arithmetic encoding. But they can be implemented in ways that get you significant speed improvements to arithmetic encoding. And because of that, right, you can approach Huffman speed while still getting the smallest possible size for your entropy. My understanding is they are still able to win with Huffman. So my understanding is, like, at RAD, the very fastest codecs they have, which are like very close to like a mem copy is how fast they are now, is that Huffman is still the one that they use on the very fastest codecs, but on like just slightly slower, they have RANS or TANS encoders. I'm not sure exactly how they work. Like I say, that's for the experts to know and me to wonder about. The very fastest ones are still Huffman, but only slightly slower now are these ones that are based on the ANS math, and those are like extremely fast and get arithmetic size, which is kind of crazy if you think about it, because I think for a long time people didn't think that was possible until some saucy gentleman, I don't know the specifics, but came up with the ANS stuff, and then either the RAD folks or somebody figured out that there was ways to exploit the properties of that ANS style alphabets to beat arithmetic encoding. So that's pretty cool, right? That's just one of those things that's like awesome. Like, how did that happen? At this point, I feel like we're kind of off. Like, this has been almost an entirely compression oriented stream. So I don't know. At this point, it just seems natural that we should just do it, right? We should just like keep it going. Why stop there? So, I mean, let's just say that, we want to do one of these, right? Let's take a look. So right now you can kind of see here we are in our Handmade hero directory. I'll just load up some code. Well, let me not load up quite code just yet. Let's just take a look at something that I'll just show an example of how you might approach sort of thing. Let's say you just wanted to play around with compression a little bit, right? Like I said, not a compression expert, so I'm not going to throw out any kind of great wisdom here. I'm just giving you like a little tiny foothold. Here's our art files, and we know that our art files are not compressed at all, right? We know that these art files that we've got, all we did was we just dumped bits into the file, and we didn't compress them at all. They're just raw data, okay? And so here we are in here. And maybe the first thing that we're thinking is like, well, should we apply compression? What kind of compression should we apply? How much would we save if we did compress our data? We don't know answers to any of this, right? Well, one thing we could do is obviously, if we wanted to know how much compression we might get out of something like test scene layer 00.bmp, one thing that we might do is say, well, if we wanted to use lossless compression on it, how small could it get? One very obvious way to do that, right, is to say, let's use someone's existing compression. So let's say I go and I open this up with a program like GIMP, for example, which is a freely available program that you can download to play with files, right? So one thing I could do is say, well, all right, let's suppose that I just save the file as a PNG, which I know does have compression, right, and it has lossless compression. Let's just save it as a PNG and see what we got. So there we go. Now I can compare these two file sizes and go, oh, look at that. Like, wow, compression would save me so much space. This is right now a 2 megabyte file that we're using in Handmade Hero, but if we wanted to, it would have only been 86K, right? So a massive difference, okay? Now, I don't know very much about the PNG format, but I do believe it's basically like an LZ with transforms kind of a thing. And we just kind of talked about LZ, so it's like, okay, well, what if I just compressed it directly with an LZ, something that didn't even know it was getting an image, but I just wanted, I just wanted it to test just a straightforward LZ-style compressor. Now, LZ 7-zip, which is what I'm going to use here, uses a thing called LZMA, which is sort of like a very advanced LZ encoder that does a bunch of very specific things. It's got different backend. I don't even want to go into it. It's got a lot of extra stuff. But let's see how that does on it. And that does even better, right? 7-zip is actually better than ping at compressing this particular file. But here you can see, like, okay, we're not going to replicate 7Z or ping necessarily our first time out because we don't know anything about compression and whatever, but odds are pretty good that an LZ compressor, something very basic, would probably still be pretty darn good here. Look at how good we can get with these. So again, one typical thing that you'll do if you're just going to start down the compression path of things, right, is say, oh, well, what could a different compressor get? What could a compressor written by experts, what could that get? Now I've got a sort of a bound on it where I know, well, if I just re-implemented, if I literally just went and learned how 7-zip worked and re-implemented it, that's what I can get. If I went and read about PNG, how that works, it's a public format, I could certainly do that. That's what I might be able to get, right? So that gives me a good target to shoot for, and that's really handy, right? Because otherwise, we might not know. Otherwise, we might not have anything to shoot for. We would have no idea if our compressor was any good or not, or what it's sort of bound, what to aspire to if we wrote a good compressor that was based on 7-zip, that was based on LZ. What would it look like, right? But this is great because this gives us something to shoot for. It gives us an idea. Hey, that's how good it could be. Let's take a look, right? Okay. So let's say that we want to do something along those lines, right? Let's say that we would like to make something that does a little bit of compression there. Well, okay. So let me go ahead and open up our project here, and I'll go ahead and build it. Make sure that we get the build loaded here as well. There's our build.bat. And so, we've got our simple preprocessor here, right? This was like our little thing that we did that kind of was a little command line utility we could use. Let's go ahead and just make another one of those, right? So here it is. Here's our simple preprocessor thing. Let's do our simple compressor instead, right? And we'll do a little CL here, and we'll say, okay, we'll call this simple compressor. And we'll go ahead and link it the way we were doing. And we don't need to run it or anything here, but we've got a simple compressor that now will compile, right? And so if I go ahead and do this build, obviously it's going to give us an error. It's going to say that simple compressor is not found, and there's a very good reason for that. We didn't actually make it yet, right? But I can go ahead and let me just copy the simple preprocessor in here and call it simple compressor, and we'll start with that. So let's go ahead and load simple compressor. Here is simple compressor. We don't actually want pretty much most of this stuff, right? We don't want the metastruct, and we don't want the tokenizer or the parsing or any of these sorts of things, right? So we'll get rid of those. But we do want to keep probably read entire file into memory and null terminate. We don't care about the null terminate so much, but the read entire file into memory would probably be a good idea. All that would involve is getting rid of the file size plus 1 bit and the null terminator, but everything else here is exactly what we might want for this purpose, right? Pretty straightforward. So now we get rid of this stuff here, and we could do our file contents, read entire file into memory, here is our file name that we're going to do. Let's say we're going to do this basic compression idea. Okay. And so what I can do here is, we can even make this be like a compressor or an actual little command line compressor that would actually do something, right? We can certainly do that. Let's just say that we want our to take 3 arguments in, and again, the way that C works is, of course, it passes the command name as the first argument, so we're looking at 4 arguments here. So let's just say we're going to make a little command line utility. We're going to print out to the standard error output if we don't get the arguments we expected, and we'll just say, okay, the usage of this thing is that you have to give me the command, and then you have to say like compress or like maybe compress or decompress, like that, and then like input and output, right? So basically, you pass compress or decompress, or maybe we could do this. Maybe something like that. Not very good documentation there. I appreciate the fact that that is not good documentation, but this is a little tiny utility. What's the worst that could possibly happen? Famous last words. Anyway, so in this case, I'm just going to pass that original argument there, right? And then we're going to go ahead and go from there. All right. So now we should actually have a thing called simple compressor that we can run. Well, I guess if I'm in the build directory, we can run it, right? There it is. And whenever I run simple compressor, I'm going to get that message that says, oh, by the way, you've got to use it like this, right? Simple compressor, compressor, decompress, and off you go. OK, so that's exactly what I wanted. Now what we have to do here is we just have to do a string comparison to see which of the modes that we're in, right? And we can, now that we know that we have the 4 arguments, we can classify them as to what they are. You know what? I'm going to switch over to this side so that my head's not in the way of anything. It's just a little bit easier for people to see. Oops, let's go here. Right. So what I can say here is like, all right, I've got an in file name, I've got an out file name, and then of course I've got a command. Very, very basic, right? So my command is the first thing, my in file name is the second thing, and my output file name is the third thing. I can then go ahead and do my string comparison. I can say, well, if the command is compress, then I'm going to do compression. If the command is decompress, oops, wow. If decompress, then I'm going to do decompression. And otherwise, I'm going to have to print out the usage again, or rather that I don't understand the command, right? And so I'll just say, something here. It's like unrecognized command. And whatever the command was, we don't understand, right? So that should be it. And again, I'm going to have to actually include some of the C standard library here. There we go. And again, I'm using the C standard library for this one, unlike on Handmade Hero, where we don't really use it. So this should be something you can compile on any ANSI C thing. We're not going to try and be Windows call directly into Windows there or anything like that. All right. So now if I call simple compressor, like so on, right? I could do compress, and it should work in theory. Oh, right. I would have to do compress foo bar, and it should work in theory. Of course, we haven't implemented anything, so it doesn't. I should be able to call it decompress foo bar, and it would work. But then if I was to call something like blah foo bar, it should say that it doesn't recognize those commands. OK. Now what we would do is on compress and decompress, now we just need to actually make these things do something. So let's go ahead and try to make them actually do something. Let's see here. If we read the entire file into memory, this will be in file. And you know what? I just realized this. I want this to actually be a little bit better than it is, right? File contents. I want to know that size, whatever that size is there. So I also feel like this code wouldn't work for anything that's greater than 4 gigabytes here, because I feel like FTL doesn't actually give me a size T. Is that true? Let me see here. I feel like FTL doesn't give you a size T. It gives you an int, right? I wish it gave you a size t, but it doesn't. So I don't think it's 64-bit. It's all right. It's not the end of the world, but Oh, the aging C++ library. Anyway, so we'll have the file size here, and we'll have the contents here, like so. And so, and maybe I'll do them char unsigned here. And I might even, just to make life a little bit easier on myself, I might go ahead and say that char unsigned is going to be U8, so I don't have to keep typing it. All right. So there's my U8, and there's my file contents. And so what I'm going to do is say, OK, we'll give back a file contents here rather than just a raw pointer. And that way, when I come through here and I say, oh, what's the result? Well, I can say, oh, the resulting file size is blah. And the resulting contents is this. Let's see there. And that way, it's all kind of bundled together, and off we go, right? So hopefully, that's all we need. OK, so real contents, result file size. Oops. And just replacing that everywhere. And then we'll read the in file here. Right. Let's see. The file name is in file name. Off we go. OK. And the other thing that I need to do is I need to open the output file as well. And so let's go ahead and do file out file equals. Well, actually, I guess, do I really need to do that yet? I guess I don't want to do that. I think I'm going to let the other ones do that. So off we go. So from here, I would also like to probably put a error message out if I can't read the file. Why not? Unable to read file %s, and then there's the file name, right? So we at least know that there was some kind of problem there, and off we go. So now we just need something that does compress and decompress, and then we've actually got our compressor. So we've got like a little infrastructure here for it. And off we go. So let's actually say that we've got that and figure out how we're going to do it. So if we want to do compression, we're just going to have a thing called compress, let's say. We'll pass it the in-file file size, the in-file contents, and then we want like an output buffer here, right? And so the question would be, how big does the output buffer need to be? Right? We want to compress maybe from one piece of memory to another piece of memory, let's say. It's an in-memory compressor. So if we want to compress this way, where we take an input file and then we send to an output file, we need an out buffer here. And so we need some way of knowing how big the output buffer is going to have to be, right? So when we do our malloc, we need some maximum size here. And usually the way compressors do this is they have some idea of how much they might inflate the thing to, right? How big it would it might become when they're processing it, right? And so we'll also pass maybe the out buffer size as well here, but we'll just say, OK, so we've got an out buffer size, and then out buffer size is get maximum output size for whatever this input size is. Right? So we're just going to say, hey, one of the properties of our compressor is getting the maximum output size. Is getting the maximum output size of, and maybe I could say get compressed output size for some given input size. So the input size and the output size, we're just going to say this compressor can tell you ahead of time this is what's going to happen. And so what we could do is say, well, maybe the maximum it could ever be is like twice as big or something, right? And we'll be able to know what that actually is once we write the compressor in a second here. But we'd basically said like, oh yeah, it can't ever be more than that or something, right? To do actually figure out the equation for our compressor. But that's really all we're talking about here. It's just like, hey, output size, we need something, right? So we'll say, OK, whatever the compressor says the maximum size this thing could be, we'll actually do that, and off we go. So then we'll malloc the out buffer size, and off we go. So at that point, we've got the out buffer, and we're ready to compress, and here we go. Similarly, in this case, we would have, when we go to do our decompress, right, we need to do the opposite thing. So we would have something here that's like, decompress, and that's again going to be the in file size, in file contents, and then the out buffer size, the out buffer. Again, the problem is what is the maximum output size? And again, in this case, let's just say that, all right, whatever the out buffer size is here is get output size, or get decompressed output size. And what we'll do is we'll just say, oh, hey, compressor, I'm assuming that you put something into the stream that lets you know how big this thing expands to, because that's just a property of the thing that we want, for example. And so, you go ahead and you tell me how big this thing should be. Now, I don't always actually like that. In fact, to be honest, maybe I don't really like that at all. So what I might do is say, let's do that slightly differently. Let's say that's a property of the sort of the outer layer. So maybe what we'd say here is like, OK, yeah, let's just say that we, this file contents here, let's just say that the output contents always includes a size baked into it, right? So, since we can only do 32-bit wide things in here anyway because of our ftel or whatever, let's just say that in the outer area of the code, we remember that particular piece of information. So what we do is we say, like, OK, we know in here that we want to malloc the output buffer size plus 4 bytes. And when we do the output buffer, we tell it to compress to 4 bytes in. That means at the end, right, when we get our size t, like compressed size here, what we can do is just store the compressed size into the output buffer. So here's the output buffer. Let's just say that the first pointer to it, right, is an int unsigned, first thing there. So I'm just going to write the compressed size in there. OK? So what that means here is we can also say, all right, let's assume that the file size here is greater than 4 bytes, right? Or it's got to be at least that. If it's not that, then it probably wasn't our file, because we know that we always output the size first. Invalid input file, something like this, right? And so we take a look and we say, hey, this thing's got to be greater than 4 bytes. If it's not, then we should warn the user that, hey, this is probably not a file that we output. We don't output 3-byte long files. So we take a look at the file size and we say, OK, the output buffer size in this case is just whatever the in-file contents say that it is, right? Because we're just reading this. We wrote out this 32-bit value here, and now we're reading this 32-bit value back in that we wrote out. And then we say that's how big the output buffer is that we wanted. Off we go. So we allocate that for our output buffer size. And there you can see that happening. And when we come in here, we say, well, all right, now when we pass in the contents, we just want to skip that 4-byte value that we had there, right? And off we go. So that's all we need to do. Then we can decompress. And of course, when we actually do the decompress, we want, in both these cases, to actually write to the output file as well. And so what we can do here is we could actually say, if we wanted to, we could have a thing here that's like output, final output size. And I guess that actually could be right here, and output buffer. And so in this case, we'd just say, all right, our final output size is whatever the compressed size is plus the 4, right? Right, because we allocate the maximum we would need plus the space for the number. But then after it's compressed, we only actually now need the compressed size plus the 4, right? We don't need to write out the whole buffer. So our final output size is just the compressed size plus our header size, and we're done, right? And our final output buffer, in this case, is just the out buffer. Same exact thing is true in this case. We know exactly what the output buffer size is. It's going to be this. It's not going to have any adjustment to it. And the output buffer is here. And that's it, I think, right? So now we've just got a case of like, all right, let's go ahead and finish the scaffolding. So we've got a thing that's like compress. We've got a thing that's like decompress, right? And now we just need to actually fill these in with some actual logic. So we have the in size and the in, and then we have the out size, and the out. And then for the decompress, we've got same thing. OK. So obviously, if we wanted to, we could just start by making this a non-compressor, something that literally is worse than a compressor because it actually stores the size as well. But just for our own testing purposes, make sure that our scaffolding works OK. Let's just go ahead and say that we copy the in size from the in to the out, and then we just return that size, right? So in both cases here, and I guess our decompressor, doesn't need to store anything because it's just already a given, right? So this is now the entirety of our right. We just want to do something very simple here, where we do a copy. So if that's the entirety of our compressor, right, it's not doing anything. It's literally, just a direct copy. So in this case, again, we are sort of saying we're limited to kind of files that are smaller than we might like here, but that's because of the C runtime library. We can't actually get a 64-bit size out of everything. So what are you going to do? That's just the way it goes. But anyway. Go. At this point, we should be able to now just use that final output to actually write the output file, and then we should be done. So assuming that we got to here, right, we could say if there's a final output size, or rather buffer, then what we can do is say, all right, let's try to open the out file. Again, we'll just, do a standard. You know what I should mention? When we read this, we want to read in binary. We don't want to read in ASCII. Otherwise, we'll get the C runtime library will do weird translation to the data. So we're trying to read raw data here, so we can compress binary files, not just ASCII files, certainly. So what I want to do here is open an output file for writing. Hopefully, we can load that output file. And then I just want to do one giant fwrite to the output file. Where we write that output buffer. So the final output buffer. I never remember which of these is the one we actually want, because it has two parameters. It considers writing in chunks. So it's like this times this is the actual size. And it doesn't really matter which one you put in which position, but it has to do with how it reports the write if there was an error, which we don't care about at the moment. But like I said, it's always a little bit weird. Anyway, so when we do the fprintf here, we just want to say unable to open output file like this. And we just say, oh, that's out file name. OK. So in theory, that's a complete simple compressor, right? And so here's our simple compressor that we can run now. And it doesn't actually do any compression yet. So let's go back to our data directory here. I'm going to say, oh, well, you know what we could do actually? Well, no. I'll go ahead and just copy something from the Handmade data directory. I don't know, let's see, test1.hha, for example, and we'll copy it here, right? So there's test1.hha. It's 1.5. megabytes long. And so if I do simple compressor on it, and I say I want to compress test1.hha to test1. Like simple compressor, I don't know, compressor, something like that. Oops, and I forgot a command. There we go, compress. In theory now, it should write out a file for this, and that file should be exactly 4 bytes longer. And hey, take a look, that's exactly what it is, right? Because remember, we stuck the length on the beginning, and then we wrote out the data exactly as it occurred. Now I should also be able to do a decompress on that from test1.sep to test1. Like, let's say, out, right? And now I should get back the exact same file size, and I do. And we should verify as well that I can actually, do we have like any kind of diffing utility on here by any chance? Beyond compare, there it is. So beyond compare should be on here, I guess. WinDiff, I would prefer WinDiff, but I don't think it's on here. Oh, it is, there we go. Because this one's freely available. It's from the Windows SDK if you want to try and get it, although it gets increasingly harder to get these things. They move them around, and I don't know where they are anymore a lot of times. But let's take a look and see if they're... I think this can do binary files. If it can't, we'll use beyond compare. But anyway, we want to make sure that these two files are the same. So we want to do test1.hha and then test1.out, and we can see that the files are identical. And that's what we wanted, right? So good. So now we know that our compressor can do a round trip. Now the question is, can we actually add some compression, right? And we've got some time here, right? I think you know what? I don't know when we started. 30. We got a few minutes here to do very simple compressing. So let's say here in our compressor, let's say that we want to do like an RLE compressor, right? And what I can do here is actually make a couple of different kinds of compression. Even if I wanted to, I could do something here where we said like which kind of compression we were using, which maybe I should have put in a little bit more of a concession to that at the outset. But let's just say we're going to do RLE compression for now. So what we'll do is we'll say static. I'm just going to copy this thing, RLE compress, and RLE decompress. So we've got these two now, and what I'll say is like, OK, we're just going to forward these for now. RLE compress in size in, out size out, and RLE decompress in size in, out size out. And that way, when we actually do this compression, we can actually have something that sort of does different kinds. Well, we can try by just swapping it out. And probably I should put a little format code in there that says, oh, here's what the compression is, and so we can pick between them or something. We'll do that later. All right. So if I do RLE compress here, this is the thing that Miblo is working on. For example, let's see how we might do that. OK. So what I want to do here is say, OK, I'm going to go through my stream. And I'm just going to write this the simplest possible way, right? Nothing fancy at all. And I'm just going to say, like, OK, I've got my my stream pointer. So this is my where I'm at in the stream. And I want to iterate through all of the characters in the stream, let's say. And for every character in the stream, I want to see how long of a run I have for a particular value, right? So I want to RLE compress this. So I'm just going to say, like, OK, I'm then going to say, size t offset or something like this, and start at 0. And then my offset is going to be less than whatever the in size is minus the at. So I'm going to basically say, like, let's run through every character. And for every character, I'm going to run from that character all the way to the end of the stream. Now, I'm not actually going to do that, right? I'm just going to sort of say, hey, set up the loops to do that. I'm going to break out early, so it's not actually a problem, if you will. And then the other thing I'm going to do is say, well, this ++ at, I probably need to work with that a little bit more specifically. So I'm just going to move that down here for the moment, right? OK, so I'm going to go through these streams here. And what I'm going to do is exactly what I sort of said before. I'm just going to look to see how many of the same value I have in a row, right? So let's say I'm at this particular location, OK? So I've got my value, my starting value, let's say. That's whatever's in the input at this location, right? That's all it is. Whatever's at the input in this location, I'm going to go through here, and I'm just going to say, I want to count up how many of these things there actually are. So I want to say something like, and I probably, let's say we do something here. In fact, we could just make this run, and then just say while, the offset is less than this, and the starting value sorry, just organizing this here. So while the offset is within range, so I haven't exceeded the end of the buffer or anything like that, and whatever I'm at right now, so at plus offset, while it equals the starting value, so meaning I'm still seeing the same value that I was seeing, then I want to increase my run, right? And I can just make run be the variable here, if you will, right? Okay, so I start with a particular value. That's whatever at the input stream at this point. I say, I'm going to see how much of a run I could encode here if I want to encode a run. I say, while I haven't hit the end of the buffer, let's just see how many times I see the starting value. And I increment my run count, right? Now, when I get to the end here, now I know how long my run is. And I could say, all right, this includes the run of 0. So basically, my run, I know my run has to be at least 1, right? In fact, I could just do this, right? I could just say, hey, I know the first time it's going to be equal, right? I mean, duh, And so all I really want to know here is how long, how many can I go beyond just the 1? And so then what I could do here is say, like, OK, let's see what happens whenever run is greater than some value. We'll think about that, what that should be in a second. But let's say as long as it's greater than 1, we'll just encode every run, let's say. As long as the run is greater than 1, then I want to, encode a run. Otherwise, I want to encode literals, right? OK. So let's think about what has to happen here, right? Because we're going to kind of work this loop through a little bit. So if I was going to encode a run, or if I was going to encode literals, I kind of have a little bit of a problem here. I need to know a little bit more about what I need to know a little bit more about how I'm going to actually buffer these literals up. Because if you think about it, if I encode a run, well, I could just output a run right here. I'd say, here's the run value, which I know, and here's the value that I'm trying to encode, which I also know. No problem. But if I'm trying to encode literals, I need to buffer them up, right? Because I need to know that I'm putting literals into the stream here. So what I need to do if I'm encoding literals is I need a buffer. I need something that's like my literals buffer, right? And my literals buffer needs to have room to store as many literals as I might total, be able to store. Something like this. Right? Because the number of literals that I might have is however many I might have. And I might be able to store 255 literals are coming. I need to be able to write 255 literals into my buffer here, right? So I need to have something like this, where I just have, OK, here's the literal count, and here's the buffer for the literals, right? And I could undef this. OK? So if I want to do something like that, then it's like, OK, if I wanted to encode a literal, then all I would do is say, all right, when I want to encode a literal, I would say, hey, let's go ahead and put that into the literal buffer. Otherwise, I need to encode a run, right? And we'll see how I have to encode a run in a second. All right. So that's really all we have to do there. And I guess I need another thing here. This is out at. Maybe out size. Right. OK. So if I need to do this now, I need to start actually thinking about the encoding. I need to define how I'm going to encode this, right? And for starters, let's use the simple encoding that I was talking about before. So let's pop over to the decompressor for a second and just write it, because that will be the definition of how our output stream works, right? And so what I'll do there is just say, OK, I know that I'm going to continue going, let's see, in at 0. As long as I haven't consumed the entirety of the input, I'm going to keep going, right? So then all I need to do is say, all right, I want to take a look at the value that comes in, whatever that value is. So I'm going to say that the thing coming in is the literal count, let's say. So I'm going to read a value that's how many new bytes I'm going to encode. I'm going to go ahead and run that literal count down. I'm going to say for every literal that I was supposed to do, I'm going to put something into the output stream. So this is the copy, right? For every literal, I'm going to copy from the input stream into the output stream. Then I'm going to read a replication count, right? And then I also need a replication value, right? The value I'm going to replicate. And then I'm, again, just going to run that down. OK? And there's an RLE decompressor, right? That's the stupidest possible RLE decompressor we could have. All we're doing, right, is, in fact, I can even make this even simpler. We don't even need in at all, right? I could just say that the end of the input is just the start of the input plus the size you told me. And then I can just say, keep reading until in as long as in is less than in end, then we're still reading, right? And assuming this was a well-formed stream, we're not really doing anything. We're not being, we're not being robust here. So this is easy code to crash, certainly by feeding it bad data. But let's just assert anyway for our own purposes at the end that we actually consumed the right amount of input, right? But there's our decompressor, right? Very, very simple. Read in how many things to copy that many, read in how many things to replicate, and then if we haven't hit the end of the data, keep going, right? OK. So off we go. So every time we get sort of a run or anything like this, or literals or anything like that, we always have to encode a pair, right? So we're always encoding a pair of literals, and we're always encoding some number of literals and some number of replications, right? That's just how we've defined this. And I'm not even saying that's a good way to do it, right? I'm not saying this is a good RLE compressor. I'm just saying here's an RLE compressor, right? Because another way to do it would be to have these be bit coded. So like, for example, we use 1 bit in this value to say whether it's a run or a copy or whatever, right? But we're not going to do that. So what we do is we say, all right, values come in. We see how many there are. If what we're on is a run, then we need to encode the run. Otherwise, we just buffer the literals, right? And so all I'm going to do here is actually have this be the encode flush. Basically, this is going to be the thing that actually does the encoding. So what I need to do is I need to match whatever I was doing in this output, right? So I need to do a thing that basically says, all right, the output is going to literally be exactly this thing. So I need to maybe I'll do literal index. I need to go over my buffer, and I need to output it, right? So what I would do is I'd say, let's output the literal count, however many literals there were, and then I need to output the literals, right? I know once I've done that, my literal count will be 0, because there's nothing left in the buffer. And then I need to output my run. So then I say, OK, whatever the run length is the run, and the starting value I know is whatever this starting value is right here, right? Right? So that's it. That's all I have to do there. And then encoding literals, I just kind of go ahead and put the literals in. Now, there's one more thing we have to deal with here, but yeah, that's basically the way it goes. OK. So let's go ahead and deal with our at handling here. Our at handling, like kind of as we're going through our in buffer, basically when we look at these runs, when we're kind of looking at how far we've gone. Run-wise, all we want to do there is say, well, OK, if we encoded a run, then we obviously moved that far in the input. If we encoded a literal, we only moved one, right? Does that make sense? So we want to kind of advance the input differently depending on which one we did here. OK. So there's one more thing we have to take care of here, and that is that we don't have unlimited size, right? When we go here to encode a literal, we can only actually encode a literal if there's room left in the literal buffer. So when we're going to encode a run, really what we mean here is we need to flush the literal buffer both in the case where we want to encode a run and in the case where we have no space left, even if there is no run, right? So what we want to do here is say more like, well, if the run is greater than whatever our run length value is, or the literal count is equal to the max literal count, because we couldn't put a single we couldn't fit any more in the buffer, we have to flush, then off we go. Right? Hopefully that makes some sense. I'll go over it one more time in case it doesn't. But anyway. So in this case, again, we have to output the literal count. What we want to do here is probably assert that the literal count, I guess we could say like literal count 8 equals u8 literal count, and then just assert that literal count 8 equals literal count, like meaning guarantee that we can fit it in the space we're actually trying to fit it, right? There we go. And then the same thing would be true for the run length, right? Same thing here. True for the run length. Run 8 equals u8 run, assert run 8 equals run, right? I guess I should say buffer literals. All right. So last thing we have to do, again, so this part right here is designed to make sure that, hey, we can only store a value from 0 to 255 for how many literals there are, so we can't go above that number. And similarly, exact same thing is true for our run. So if you take a look at what happens here, we've got this run is less than in size minus at. That's assuming we can get to the end of the buffer. But we can't necessarily get to the end of the buffer because we could only encode a run of 255 at maximum. So we could adjust this value. I'm going to be lazy and not even bother adjusting that value. I'm just going to say, and the run is less than max run count, right? Which again is exactly the same, max run count, 255. And this is less than or equal to there, right? Because we could actually encode 255. So then we'll come in here and just undef those two, max run count. OK. So there you go. And that's just, again, to make it so that we don't end up with a value that's too big for us, right? So, hey, yeah, did I type that in extremely quickly? Yes, I did. So, probably got some bugs in there somewhere. But let's just go ahead and sort of take a look at how that's working in the debugger. So I'm going to open up msdev on simple compressor.exe. Give it a second, because as we know, Visual Studio takes many years to load. It has to do all kinds of wonderful things. I'm sure they're really important. So let's go ahead and open up the properties for simple compressor. Here are the executable. We need to pass it that information that we were passing it before, right? We need to give it a valid compression rule. Where is that? Not decompress. I want compress. There we go. OK. And so I'll paste those in there. So we want to pass compress and these two values. We want to be in the build directory. That's where we were doing this, so that's fine too. So let's go ahead and step into this. Right? Let's go ahead and see how this works. So it's exactly, all this stuff is kind of rote. You've seen it many times before. So we're going to go through. We say, OK, what's the command? The command in this case is compress, right? So let's load everything in. Oop, I didn't mean to go that far. Didn't mean to go that far. Stop. Meant to jump in here. There we go. So here we go. We start out in the compressor, and now we have to go ahead. And it looks like we had a bug there, so we're going to get to debug this thing. But I just want to kind of step through it first once to kind of see how we were doing with it, right? Yeah. This one could actually also be done exactly the same way as the decompressors. In fact, I might go ahead and just do that because we might as well have them look a little bit more symmetric. That's basically like this sort of thing. So that's basically just, again, like we just always want to read from that particular location. So in this case, we can sort of set, take our ats there, and we can just use just the actual location without having to do this, right? So we can basically just say like, all right, the starting value is always going to be, wherever we are within, right? So this is in 0. And then here we're just going to be looking ahead, run numbers of things. And then when we actually increment, we'll just increment the actual in pointer, right? So that seems reasonable to me. OK, and so then again, this also becomes just a subtraction where it's like, hey, make sure we're not looking off the end of the buffer. Right? What are you complaining about? Which one are you complaining about? Signed, unsigned mismatch. OK. Is that because size t is unsigned, I guess? It's OK because we know these things should never invert. But yes. All right. So let's go ahead and go in here. So here we go. And let's just take a look at where we are with the in value. So here's some information. So it just so happens that the first byte happens to be replicated, right? Because HHAF, that's actually the data in our HHA file. Remember, that was, I guess, what was actually there. And then there were some zeros. Let's take a look in memory, actually, so we can actually see what this is. There you go. So you can see the HHAF, and then there's some zeros and other information. This is the stuff we're actually compressing. So hey, it looks like the first thing, there was actually a run count of 2. Now we break out of here because the next thing is an A. So we could encode the H as a run of 2, but we can't encode the A as a run, so that would have to switch to a literal, right? All right, so off we go. We look in here, and right now we're encoding runs of any length, right, just as a test. And we'll talk about that a little bit later, but if you think about it, a run of 2 long might not be worth encoding because it requires a flush of the literal buffer, and you didn't save any space because you had to encode the count for the run as well. So that number might be more like 4, let's say, to actually talk about more optimal encoding. But anyway, ignoring that for a second, here we come in. We take a look at the literal count, and we see that it's 0. So we store that 0 as the output, right? And then we don't actually encode any literals because, hey, there was nothing in the buffer. We then say, hey, there's a run count of 2. So we output that run count of 2. And then we output the value we're actually trying to do, which is the H. We then move forward by 2 things in the input because we consumed those. So now we're on the AF, right? And then we go back to the beginning. Again, in this case, there's no run. It's just an A. So then we buffer up the A, and we say in our literal buffer, and we can see that getting an extra thing here. You can see the A there. It adds that A to the literal buffer, and we've got a literal count of 1 now. Right? We advance the input by 1 because now we've consumed that literal, and we start again. Right? There we buffer another one. And we just keep going. Now there's some zeros, right? There was a bunch of zeros, 4 zeros. We say, oh, OK, let's take a look at the literal count there. The literal count in this case is 4. So wait. Oh, no. Oh, wait, no, that's fine. That's the literal count. Never mind. I was like, what's going on? No, the literal count, that's fine. So we encode the 2. Then we encode the 2 literals, right? There's the first one. There's the second one. And then we reset the literal count to 0. So that's what we want. We then look at the run count, which is 4. We encode that run count of 4. And we encode the starting value of 0, right? Because it's just a 0 that we're copying. We then advance the input to skip all the zeros, and we get to the next thing. And off we go, right? So now let's see where we were getting the problem. We hit an assertion. I'm assuming it's this one, but it could be another one of these in here. Let's see which one it is. We try to debug. What is this? Where are we? In the call stack, RLE compress. So it looks like we ended up with a run value of 256. So, that's good. Yeah, that was a mistake. That's just a really simple mistake. So this run count here, you can see I did a less than or equal to max run count, and I was dumb. It wasn't less than or equal because we're about to increment the value, and we can't increment the value once it hits 255, right? So that's actually wrong. That's good. Thank you, Mr. Assertion, for catching that for us. There we go. So let's try that one more time. And so here's our output size. Oh, right, and our output size, we need to actually compute that. Again, this is best done with pointers. So what we can do here is we can say, let's just remember where we start, and we'll just do our output. So then at the end, we can say, instead of like tracking the output size, which we don't want to have to keep an extra thing around, let's just say, OK, we'll take the output size. The output size will be equal to the out wherever we were in the output minus the out base. And then we'll also assert that the out size is less than or equal to the max out size. So we didn't overrun the buffer, because that just means we have a bug. Right? All right, so let's go ahead and run it. We ran it, and that's actually doing our compression. So here you can see the actual results of the compression, right? And it looks like, wait, there's no way that could be right. It couldn't possibly have, hold on a second. Couldn't possibly have outputted the exact same size with a totally different compressor, could it have? Are we not using the output size accidentally? Compressed size +4. It looks like we are. Is that really true? Let's take a look. What happened there? Compressed size. How is that? OK. Am I nuts? I must have done something stupid. It seems impossible. It couldn't happen to end up at exactly the same. That's insane. There's just no way. Hold on. This is one of those like, hey, I'm on stream, so I'm not paying close enough attention kind of things. Got to be, right? So there's the output size, right? Out minus out base. So let's see here. In size, out size. So the in size and the out size are like nowhere close, right? They're not even remotely similar to each other, right? OK, so we're going to return that value. Right. When I did my forwarding, I forgot to actually use the value. OK. Now we're a little bit better there. All right. So OK, now if I actually run this, we have our compressed output. You can see now that it's much, much smaller, right? It's about a tenth the size. So that's great. And now the question is, well, did it work, right? And so let me delete test1.out here. So there's our HHA. Again, it's 1.5 megs. We went down to 0.2 megs, a little less than. So that's great. About one point, well, you can see the numbers yourself. I won't try to English translate them. So if we go ahead and write simple compressor and we do decompress, right? Then I take my test1.scp and my test1.out, and now it does the decompression. And good. And my decompressor doesn't work at all, so that's always good. So maybe now's a good time to switch over to actually debug the decompressor. Hold on for a second. So let me go ahead and switch to the decompressor. So let's do decompress test1.scp to test1.out. There we go. Right. Let's step in there. And let's go ahead and take a look here. So we step over to the file size. We take a look at the out buffer size. That's not right at all. That's another bug. You can always find bugs when you step through your code. So I said that I was going to store the output size in here, but I didn't do that, right? So I need to store, I stored how big the file was. But we don't need to store how big the file was. We already know how big the file was. I need to store how big the original file was. So that's supposed to look, oh, sorry, not that. I need to store this piece of information. I need to store how big we're going to produce, not how big we ended up being. So that's just a compressor bug, or rather the wrapper for the compressor was just wrong. All right, so let's try a simple compressor test1.hha to test the CP, and we'll do compress. There we go. And then we'll do simple compressor decompress test1.scp test1.out, and we're still not good. Okay, let's try this one more time. Out buffer size. Now the out buffer size. Wait, that's still wrong. Did I not recompile that? What just happened? Well, I thought we wrote to the out buffer. Oh, God. Wow. How many? You know, the typo situation here is interesting. It's supposed to be file size. I need to pay closer attention here. Let's try this one more time. Okay, so I'm going to step in here and see what actually is happening. Okay, so we go ahead and we do our compressor. We produce the compressed size, which is this. We have the in-file file size, which is that. And I'm trying to write to the output buffer, which is what I'm going to output. Here's my output buffer, right? And let's just see what the size is that we actually stick in there. So there's what's in the output buffer right now, which I believe it should just be garbage, right? Because we didn't actually write anything to it yet. We write in there, and there's our actual value, 1.5 megabytes, which is what we want. And we basically say that the output size is what we used plus the 4-byte little header bit there, and then we say the output buffer is the out buffer, right? So here we come into final output buffer, and we're going to write this thing. So we should be able to verify that the exact same thing is in there. So here's final output buffer, right there it is. And then we go ahead and do our fwrite. I should have probably checked that return value, but I didn't. So that's fine. We get you can see we actually did return it there. All right, so the fwrite looks like it's succeeded, and so then we're done, right? And that should have written to our output file, right? Then, if I step in here for the decompress, right, which I should be able to do, let's go ahead and I should have a decompress. I should have something that does decompression and compression, so I don't have to keep doing it. I don't have to keep typing these things in. But so if I step into the decompress, and now I do like, all right, I'm going to do my decompress. The content should show me here, and there it is. All right, so I don't know why that wasn't working before. I guess I must not have actually compiled it or something like this, or I must not have actually run it properly. But all right, so there we go. And now our decompressor works just fine. That we actually pass it the correct size, and then we have our output buffer, and we write it. Okay. All right, so I don't know what I did wrong there, but I did something wrong in terms of running the program, not the program itself. And so let's see what we got. So here's our test1.hha, here's our test1.out, and now I should be able to do our windiff. Now I don't know why I can't run windiff. It's not in the path, I guess. So let's just take a look at where it actually is. Okay, so it's in this long path here. we go. So let me go ahead and copy that, and then I will go ahead and paste it in here. And so now I should be able to do test1.hha and test1.out and see if they're the same, right? And it looks like the fact that it was loaded would suggest that it wasn't the same, but let's see. Oh, no, they are identical, right? OK. Hey, so congratulations. We have a compressor now, right? It's not a very good compressor, but you can see it gets a lot of compression on that file. Let's see how it does with the whole HHA, right? So that's our simple compressor. Let's say we went over and copied out of Handmade Hero the intro art.hha. So that's a much bigger file, right? Intro art.hha, that's about half a gigabyte, right? And so let's do simple compressor, compress, intro art.hha, intro art.scp, right? And this, probably in, if we were actually trying to make something real, we'd want to print out a little like %done indicator. But there we go. So we take a look at it and we see like, oh, OK. The intro art, even with our really, our super simple, very basic, not particularly interesting compressor, you can see that intro art.hha, intro art.scp, intro art.scp got much better. We saved, an entire 140 megabytes there, right? 140 megabytes just by RLE compressing this thing, right? Which is, extremely stupid. We didn't even do anything really to make our RLE compressor be particularly well tuned in any way. But hey, that's really great, right? So 100 extra megabytes, awesome. And we could probably do much, much better than this, like I said, by doing something better. So maybe tomorrow I'll show you how to do LZ, which should, again, save us even more space. But it's still not really the kind of thing we would necessarily use on this. But all right. So let's go ahead and go to the Q&A. And like I said, this is just, that's like the dumbest possible compressor we could make, right? It's like, it's not, we have done nothing, right? But it just so happens that this data that we have here is very, very easy to compress because, hey, it had lots of empty space, right? Like, why is this compressor, I say it's a bad compressor, but you see, look at how much it compresses file. Well, keep in mind, that's because this file probably had hardly anything in it of consequence, right? So, it's a bad compressor because you take a look at, where was that? Test1.hha. Let's see what happens if a real compressor comes in here, right? And we add it to 7z. And you can see like, OK, 7-zip took our output and it like made it twice. It then did another 2x on top of that, right? So we only took out the low-hanging fruit, but you could still do a lot better. And similarly, on anything that wasn't so regular, 7-zip would crush us, right? Like we're only happening to benefit here. And you know what? We could probably demonstrate that because here's our output file. I bet if we compress even this one with 7-zip, it'll probably crush us, right? So here we go. We'll let 7-zip do it here, and we'll see how big 7-zip manages to get this file with the same thing. And it should just annihilate us, right? It should just absolutely trounce us. All right, some questions here. Mibla says, awesome stuff. I hadn't been making the distinction between literals and runs in my thing. My test stuff has just been zeros and ones mine, so I was just storing the first token and then the counter values. OK, yeah, so that's an interesting point. So yeah, basically, this kind of RLE is the kind that I grew up with. Again, so that's why I did it first. But yeah, Another way you could do it is just store a count and then a value, a count and then a value, and a count and a value. And in that case, your literals become just a 1 and then the value, a 1 and then a value, a 1 and the value. The problem with that is a lot of times you have a group of values that you want that are all different, and you keep inserting all these 1s, you like double the size of that, right? So what this allows you to do is kind of take advantage of the fact that typically if you see new values that aren't runs, they tend to be a bunch together, right? And so that just helps. It tends to be a little bit better. Like I said, the other ways you can do this are you could have a 1 bit in the run encoding says whether it's literals or regular. So then you can only do 127 of them, right? You divide your number in half, and then but you can say for each one which kind it is, literals or runs. Magic 603, what I was saying is tomorrow I'll show you how to do simple LZ instead of instead of RLE. So just a different type of compression. So did 7-zip finish? Yeah. So take a look here. You can see here's the HHA that's our data file for the intro cutscenes. Here's the SCP file, which is what we did with this is an RLE encoded version, right? And here's intro art.7-zip. Intro art.7-zip, look at how much smaller that is, right? Than ours. You know what I'm saying? It's way better. It's only 80 megs, whereas we're 320 megs from an original of 462 megs, right? So 7-zip just absolutely crushed us, right? So, I just wanted to make that point because it made it look, test1.hha has so much giant blocks of zeros in it probably that it made our bad compressor look a lot better than it should have. This looks amazing when you look at it. You're like, oh my God. And 7-zip can only double us from there. It's like, no. Most data, 7-zip is way better than double, right? What we would do with an RLE. So. TTBJM, are hardware image decompressors still a thing? So I guess I'm not sure I understand what you're asking, though. I guess I don't understand the question. So the first thing I'll say is most 3D games anyway, and 2D games may not for various reasons, but for most 3D games, because you're using textures in a way that tends to end up being like filtered and it's with lots of shaders layered on top of it and all this stuff, you tend to not need lossless compression. You can be a little bit lossy. So most games nowadays that are in 3D, and some that are in 2D, depending on, again, the circumstances, do use very simple texture compression that is implemented in the hardware, which is essentially a way of encoding usually 4x4 pixel blocks, but that's not the only kind. But usually including 4x4 pixel blocks by encoding them as something along the lines of, let's say, 2 base colors, and then each pixel just says somewhere between one and the other base colors in like increments of like 25% or something like this. Those sorts of things. And hey, if the value can't be encoded that way, then it just is wrong. It's lossy. It's totally lossy. You're absolutely in no way guaranteed to get anything close to the original image back. But it's just like, it's an approximation, right? It's a way of storing, it's a way of putting textures into a smaller space that is reliably decodable on a GPU that tends to have not too objectionable artifacts when the textures are being used in 3D for multiple shaders, layering, and that sort of stuff. There's enough other things on top of it that you don't tend to notice the artifacts. right? So if that's what you mean by hardware image decompressors, then yes. If what you're talking about is more like JPEG or something like this, with a discrete cosine transform and stuff like that, then the answer is more like yes and no. Games, generally speaking, aren't doing anything like that. Games, generally speaking, aren't compressing their textures with like DCT that gets decompressed in hardware or something like that. That's not really a thing. And the reason that that's not really a thing is because games typically don't care so much about how much space textures take up in main memory. They tend to care more about how much they take up on graphics card memory. And since the graphics card needs the textures to not be DCT encoded in order to use them, you tend to not care, right? So you tend to have to store the textures on the card in the format that the card can read, which it can't do DCT in real time yet. Meaning at the speed it needs to do it to texture from that. Now, I guess I don't know how true that really is, because I don't know if there's maybe some cards that are experimenting with that sort of thing now, but in general. So, if you were storing those as 8x8 DCT blocks or something like that in main memory, you could just have the DCT done by the CPU in the background before uploading the textures or stuff like that. Stuff like that might be happening, but typically speaking, you don't send down the things as DCT'd and then have the hardware do the un-DCT, typically. Again, not to say you couldn't, right? It may be that a game at some point, and I don't know, I'm not up to date on what maybe Battlefield 1 or some advanced engines these days are doing, but you could imagine implementing something like a DCT with a compute shader and then doing your uploads in like something like a JPEG format and having the card do the un-DCT into the DXT format, but that involves all sorts of other things and blah, 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 right? So there's a bunch of things you could imagine doing there. Which ones people are and aren't doing, I'm not comfortable with saying. So that's the no part of the answer. The yes part of the answer is for a bunch of stuff like video, where you're just talking about one thing that's being round-trip decoded or encoded, so like MPEG-4 or things like this, there still is a bunch of stuff in hardware for that oftentimes, right? So certain parts of the decompress for things like the MPEG-4, like the DCT or the MoComp or whatever, depending on whether you're compressing or decompressing, blah, 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 that sort of thing may be being done in hardware for video, depending on, again, the circumstances. And I'm not, again, up to date on what everyone's doing everywhere, so I'm not comfortable saying who is and isn't using that and when it isn't being used and blah, blah, blah. But it's definitely the case that that sort of thing is still happening in hardware, depending on the circumstances. So absolutely. And so depending on what you mean by hardware image decompressor, the answer is yes or no to varying degrees, and it depends on who you're talking about and so on and so forth. But keep in mind that basically there's a wide spectrum there, and I think pretty much everywhere on the spectrum there's probably someone somewhere doing something, right? And, to what extent that fits what you were mentally thinking of when you said hardware image decompressor, the answer may be yes or no, right? Because there's different, when someone says that, they may be thinking of something more or less advanced or more and less complex, or what's happening there. So I don't know. I think that was it for our questions, right? All right, I think that's it for questions, so I'm going to go ahead and conclude. Or try to. Okay. There we go. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can follow along and play around with it. We also have a forum site you can go to ask question, a Patreon page you can go to if you want to support the video series, a schedule bot, which on the moment needs to be upgraded because it used to be weekday streams, now they're weekend streams, so soon that will be back to telling you what the schedule is, but at the moment it's a little bit not upgraded yet. And we have a past episodes guide you can use to catch up on older episodes that you may have missed. That's about it for today. I will be back tomorrow, and I'll just show you how to put an LZ compressor in there. So we'll kind of take our little compression framework and we'll just put an LZ compressor in there, and then you can kind of see like, okay, so now you kind of get the basics of the really simple part of compression, and then I'll kind of leave it up to you folks to figure out how to do more compression stuff on your own by reading and stuff like that, because I'm not going to go too much into it because, like I said, I'm not a compression person, so I'm kind of the wrong person to teach anything beyond the very, very basic parts of it. I really don't feel qualified in sort of going down any sort of deeper paths into compression. So that's about it. I hope everyone has a great Saturday. Until tomorrow, take it easy, and I'll see y'all on the internet. Take it easy, everybody.